by the preparation so far, indeed, we will see that the space of the Weil differentials of a given divisor can be described in terms of a Riemann-Roch space. More explicitly, this theorem is called the duality theorem, and which tells us for a given divisor A and canonical divisor W, then we can introduce a map from the Riemann-Roch space of W minus A to the Weil differentials of the divisor A by mapping each function to Weil differential xw. And indeed, our claim is to show that this is a vector space isomorphism over K. And thanks to this isomorphism, we can directly conclude that the dimension of this Weil differential of the A, so that means this is the index of specialty, is equal to the dimension of the Riemann-Roch space of W minus A. So first, let me observe that this mapping mu, if the definition of mu makes sense. In particular, if you consider a function from the Riemann-Roch space W minus A, we know that it's the divisor of its image, which can be written as the sum of the principal divisor x plus the divisor of the Weil differential omega, is bigger than or equal to W minus A, because X was chosen from the Riemann-Roch space, and plus W. Indeed, this is bigger than or equal to A. So indeed, this shows us the Weil differential is a Weil differential of the divisor A, because by the remark 1.5.12, we know that this set can be defined in terms of the zero differential, or the differential whose divisors are bigger than or equal to A. So that means mu maps functions into the Weil differential space of A. And mu is linear, mu is K-linear, because if you consider two constants A and B and two functions x and y from the Riemann-Roch space of W minus A, mu A of x plus by by the definition is defined as A of x plus by omega. And indeed, we can see that this is equal to A times the Weil differential x omega plus B times the Weil differential of y omega, because just by the definition of the Weil differential of this product regarding the others from the other space, by definition of the multiplication, we know that this is alpha A of x, alpha B of y, and omega is linear. Indeed, omega is K-linear map by its definition. What we get indeed the linearity of mu. And we can also see that mu is injective by checking if its kernel contains only zero function. Here note that zero denotes the zero differential. So that means for every other alpha, its image under the Weil differential x omega is going to be zero in the base field, in the constant field K. And by the definition of this product, indeed we want to say that we want to observe it for which functions this value is zero, and we want to see it for every other. And this is only possible if, if we have non-zero function x, this is only possible when v is a zero differential, and this forces only we have this equality for these functions. And if we are able to also see that mu is surjective, we are going to complete our proof because mu is going to be the isomorphism. And for the surjectivity, let me consider Weil differential from the differential space of A. Indeed, this is the subspace of the space of Weil differentials, and this is indeed one-dimensional vector space over F by proposition 1.5.9. So that means we can write omega 1 as x times omega with some function x. And since x plus the principal divisor of x plus w, and w here stands for the divisor of the Weil differential omega, thanks to this equality, we can see that this is can be written as the divisor of the Weil differential omega 1. And since omega 1 is a Weil differential of the divisor A, again by remark 1.5.12, we can see that this is bigger than or equal to A. And indeed, if we compare to left and the right hand side in this inequality, we can see that the principal divisor of x is bigger than or equal to minus the divisor of w minus a. And this shows the existence of the pre-image of the Weil differential omega 1 under mu. Then, if we have a vector space isomorphism, we can conclude that 2 has the same dimension. And finally, as an immediate sequence of the duality theorem and the definition of the index of specialty, we can state the most important theorem in the function fields or in the arithmetic algebraic geometry. This is the Riemann-Roch theorem, which tells us for every divisor. A, thanks to duality theorem, we know the existence of the canonical divisor as well, and this is unique by the definition. The dimension of Riemann-Roch space indeed can be computed as degree plus 1 minus g plus the dimension of the Riemann-Roch space of the divisor W minus A. And again, as we have seen like about 1.5 months ago, for a canonical divisor, we can compute its degree and its dimension in terms of the genus of the function field. For a canonical divisor, W, we know that its degree is 2g minus 2 and its dimension is g, because again, in the statement of the Riemann-Roch theorem, we know that if we consider the divisor A, its dimension will be equal to the dimension, its degree plus 1 minus g, plus the dimension of the canonical divisor. And indeed, this shows us the dimension is nothing but genus. And again, if we consider the canonical divisor, again by the Riemann-Roch theorem, since its dimension is genus G, this is going to be W minus W, L of 0, so this is 1. This gives us its degree as 2g minus 2. And finally, thanks to having an information about the degree of the canonical divisor and thanks to the statement of the Riemann-Roch theorem, we can again conclude that for any divisors of degree at least 2g minus 1, its dimension is exactly its degree plus 1 minus g. And in this case, this 2g minus 1 is the best possible bound for a canonical divisor, because L of g is always strictly bigger than its degree plus 1 minus g, because by the previous lemma this dimension is g, its degree is 2g minus 1 plus 1 minus g. This is in the g minus 1. So we always have this strict inequality. And even though this is a technical, I think it's nice to see the proof of Riemann-Roch theorem by using, actually without using complicated notions from the algebraic geometry. And we mainly use some more information from linear algebra and some spatial notions from the function fields. And by using these notions, we were able to give the most important proof of the proof of the most important theorem, Riemann-Roch theorem. So in the next week, we will be focused on the local components of the weil differentials, and this will allows us to introduce, probably 2 weeks later, allows us to introduce or allows us to consider a new description or the construction of the algebraic geometric codes. So this is all what I want to say. Thanks for your